Hi, welcome back. Dr. P here, and in this lecture we'll take a look at polar reactions and curved arrow notation. So polar reactions, as we talked about last time, are a particular type of organic reaction, specifically referring to how the bonds break and form. So we'll look at them in not so much in general, but we'll look at some of the general features common to polar mechanisms, and then look at an example of a polar reaction, which is the one in the text, is the addition of HBr to ethylene. And then I'll talk about curved arrow notation. So let's start by talking about what's going on with a polar reaction. So polar reactions, they feature heterolytic or unsymmetric bond breaking. Now they will also feature charged or polar species. In particular, we're going to encounter nucleophiles and electrophiles. Now remember, nucleophiles are Lewis bases, and electrophiles are Lewis acids. So it becomes important to be able to identify those, which I think most of you were able to do on the acid-base quiz. All right, so what do these polar species look like? What do the polar species look like, I should say? Charged species are relatively easy to identify because they have charges. But polar species, you need to look for an electronegative atom bonded to a less electronegative atom. And table 6.1, so I'll just write here, see table 6.1 for some common polar functional groups. And I'll go over these. I'm not going to draw them out because, well, I happen to have table 6.1 right here. So we can see one example is an alcohol. Let me zoom in a little here just so you guys can see that a little better. There we go. Alcohol, where we have our partial positive charge on the carbon and the partial negative charge on the oxygen. So that is polar. Notice the alkene with the CC double bond is symmetric and non-polar. An alkyl halide will have a partial negative charge on the halogen, partial positive on the carbon. Amine, similar to an alcohol, so partial negative on the nitrogen, partial positive on the carbon. Ether, because this is not actually a linear molecule, remember the oxygen is going to have a bent geometry to it. We'll get a partial negative charge on the oxygen, and the two carbons will have partial positive. Thiol is similar to an alcohol. What else do we have here? Let me get the next page of that table. Nitrile, again, we have a carbon-nitrogen triple bond here. Now we have, the next two are reverse, examples of reverse polarity. Normally, the carbon has the partial positive charge, but sometimes it doesn't. For example, a Grignard reagent or an alkyl lithium reagent. We have something not very electronegative. So magnesium with the Grignard reagent or lithium with the alkylithium reagent. So both magnesium and lithium are much less electronegative than carbon. So in this bond, the carbon-magnesium bond, or the carbon-lithium bond, the polarity has the electron density more on the carbon. So our partial negative charge is on the carbon and partial positive charge on the metal. So these two react differently than a lot of these other polar species. And you can take a look at other ones like carbonyls, carboxylic acids, acid chlorides, thioesters, aldehydes, esters, what's the last one here? Ketones. Notice these all feature carbon-oxygen double bonds. Okay, they're variations of the carbonyl with a partial negative on the oxygen, partial positive on the carbon. So one of the common features that we see is, let me just make a note here, note that usually carbon has delta plus in polar groups. And then the exceptions are the Grignard reagent, which is carbon attached to magnesium and a halogen, usually MgBr, but I'll just call it MgX here, or an organolithium, so carbon attached to a lithium. Okay, so again, usually carbon has, let me zoom out again here, sorry about that. Usually carbon has the partial positive charge when we have our polar groups. But again, there are those exceptions. Okay, so you will want to be able to identify Lewis acids and bases. And there are some, you can take a look at the, some of the figures here. Here's figure 6.2 showing some nucleophiles and electrophiles, different electron density maps, but remember the definition of nucleophile or Lewis base is electron rich and then Lewis acids or electrophiles are electron poor. So in general we would have, if we were going to look at our reaction, we would have A plus B minus. So A is our electrophile. How do I know that? It's got a positive charge on it. It's electron poor. B minus, it's got a lone pair, and it has a negative charge. That is electron rich. So that's my nucleophile. So I will get my curved arrow, I'll get that pair of electrons going to attack the electrophile, and now I'll have A, B, like so. And that's my new bond. Okay, so, go ahead and review the definitions of nucleophiles and electrophiles, so Lewis bases and Lewis acids, and you can practice identifying electrophiles and nucleophiles. That can be helpful. All right, so let's take a look then at an actual example of a polar reaction. Find a place to put that. There we go. Okay, we're going to add HBr to ethylene. So ethylene is this guy here. And then HBr, of course, is HBr. I'm going to draw in all my lone pairs. And they're going to react to give us bromoethane. So let's look at some features of this reaction. In particular, let's take a look at, as we can see here in figure 6.3, what's going on. All right, so I know I've got HBr, and that molecule is polar. I can actually look at my map here, electron density map, and see that the blue area is more positive and more reddish color is more negative or greater electron density. So this is definitely polar. So, you know, I could go ahead and I'll draw my, like that. So I have delta plus, delta minus. Now, my ethylene is not polar, okay, but I have extra electron density. I talked about that because double bonds, alkenes, can be Lewis bases. They can be nucleophiles. And so figure 6.3 shows that. We have, for a regular sigma bond, those electrons in the sigma bond are, they're kind of, you know, held inside the molecule. The electrons for the pi bond part of the double bond are above and below the plane of the ethylene molecule. So they're more readily accessible in a given reaction. So what exactly happens? Well, let's take a look. So what is believed to happen, or the evidence supports the following mechanism. We have a partial positive charge on the hydrogen, and we have extra electron density on the alkene, the double bond. So we're going to get that electron density grabbing the hydrogen. Now when that happens, because we can't have two bonds on hydrogen, this bond has to break. And those electrons will go into the more electronegative bromine. Now I tend to draw my steps, my mechanism steps, with these with equilibrium arrows. Just to show you what's going on. Now that will give us the following. This double bond is no longer going to be a double bond, it will just be a single bond. And now I'll have a new carbon H bond, carbon-hydrogen bond. Which carbon? Well, because it's symmetric, it doesn't matter. So I'm going to say it's right there. Now this carbon, on the other hand, is now electron poor. Well, I already made here my Br minus, and that's a good nucleophile. My carbocation is a good electrophile. So now I naturally would expect there to be a reaction where my Br minus is attracted to my C plus. A pair of electrons from that Br minus would attack the C plus, forming a new carbon-bromine bond. And there we go. So this is how we would draw the mechanism. Now, figure 6.4 shows that in a little more detail. in particular, it shows the carbocation structure. Carbocations are sp2 hybridized because the carbon only has 3 things on it. In this case, carbon, hydrogen, hydrogen. So that's sp2 hybridized, and we have a leftover p orbital, which is empty. And that then will attract any extra electron density, such as from a Br minus. And so now we'll get that reaction happening, and we get bromoethane. Okay. Now, this is just an example of a reaction mechanism. And there are some general things that you'll want to pay attention to when you are drawing reaction mechanisms. So let me get some new paper here. And let's talk about curved arrow notation. Okay, now remember your arrow with a regular full arrowhead represents 2 electrons. And then an arrow with the fishhook here, or single arrowhead, half arrowhead, whatever, represents 1 electron. Now, the arrow that represents 2 electrons, it has to start somewhere, and it always starts with a pair of electrons. So let's make some rules for drawing curved arrows. Okay. So the arrows always start at a pair of electrons, and they end up at something electrophilic. So the way that the text defines it is the electrons move from a nucleophilic source to an electrophilic sink. So arrows start at pair of electrons, and that could be a bond or lone pair. And they're going to end at a nucleus, typically. And let me just think. So arrows end at, I'm going to call it electrophilic nucleus. Or electrophilic atom. Okay. Sometimes when you're drawing mechanisms, you can end the arrow at a bond, just like you did with resonance structures. Okay, so you can do that. But for the most part, you're going to have an arrow ending at some place eventually at an electrophilic atom. Now, some other rules that the text mentions. Electrophiles can be negatively charged. They could be neutral. Example of a negatively charged electrophile could be something, nucleophile could be something like methoxide. A neutral one could be something like methanol. Now, as you might expect, there's more electron density on the oxygen of the methoxide, so that'll be a stronger nucleophile than the methanol will. Methanol will be considered a weak nucleophile. Our electrophile are either going to be positively charged or neutral. And so an example of something positively charged could be a carbocation, could be something like H3O plus. Yeah. So it's important to make sure, I really can't stress this enough, it's important to make sure that you are starting your arrows in the right place and the arrows are ending up in the right place. So remember, curved arrows always start at a pair of electrons, either a bond or a lone pair. And the arrows are going to end at an electrophilic atom. Nucleophiles are typically going to be negative or neutral. You're not going to have a positive nucleophile. Electrophiles will be positive or neutral. You won't have a negative electrophile. So let me just maybe draw some electrophiles here. So we'll do C. I'm just going to use R to represent alkyl groups. Okay, here I have my electron deficient carbon, my carbocation. R equals alkyl group. There we go. And here I've got my carbonyl, which is polar, if you remember from earlier in the lecture, partial positive on the carbon, partial negative on the oxygen. This is an electrophile. This oxygen is not nucleophilic. The carbon is electrophilic, however. After maybe we get it to react and we have an O- charge on there, depending on our mechanism, now that could be a nucleophile, but to start out with, this behaves like an electrophile. So that's one thing that you'll want to do, is as you're working through the practice problems, get used to identifying nucleophiles and electrophiles. That will be something that will be assessed. Another thing that will be assessed, of course, is curved arrow notation. And curved arrow notation will be assessed again and again and again and again. In fact, every time there's a mechanism question on a quiz or an exam or the final, there will be an assessment for curved arrow notation. And it's actually possible to, get a 4 on your curved arrow notation, but, get a 1 on the mechanism. So you could have drawn your curved arrows correctly, but totally messed up what was reacting with what. I have had that happen. So it's part of drawing mechanisms, but not the only part of drawing mechanisms. All right, so hopefully you learned a bit about polar reactions, nucleophiles and electrophiles. You saw an example of a polar reaction, adding HBr to ethylene, and then we've introduced curved arrow notation. And again, I really can't stress how important this is. And I'll go over more examples in person in our Friday meeting. All right, until next time, stay safe out there. Bye now.